Hello, in this video we are continuing what we were talking about in the previous video. So this is example 2 in section 8.7. Specifically in this video we are going to be working through part B. So we've already completed part A. We've found a power series representation for e to the negative x squared from the power series representation for e to the x, and we've also determined the interval of convergence. So now we are going to obtain a power series representation for the integral of e to the negative x squared, and notice the only difference here is that we need to integrate, and again we will find the interval of convergence. Just as in part A we used some information known about the technique, which in that case was substitution or composition. We used that to give us a shortcut with our interval of convergence. We will also do that in part B when we integrate. There's some information there we can use to help us find our interval of convergence. As I said in the previous video, you can always go back to using the ratio test, but it will take longer. So if you know information to help you save time, feel free to use it. So we are going to do part B, find the power series representation for the integral of e to the negative x squared dx, and find the interval of convergence. So I'll scroll down here to the bottom of the solution for part A because we're going to be using that for part B. So part B, we need to find a power series representation for the integral of e to the negative x squared dx. Since we have a power series representation for e to the negative x squared, we simply need to integrate that power series with respect to x. So I'm going to integrate the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over n factorial dx. Now remember, when integrating and differentiating any sort of power series, whether it's specifically a Taylor or Maclaurin series or just a general power series, we can always do this term by term. So if you'd like to, you can write out your terms and integrate each one, but since this indicates a sum of terms, I know I can take the integral and pull it inside of the sum so that you end up integrating each term individually. So I'm going to rewrite this as the sum from n equals 0 to infinity of the integral. And in fact, I'm going to do a little bit more than that. Negative 1 to the n is not dependent upon x, neither is n factorial. So those two can also be pulled out of the integral, like constants being pulled out of integrals. So we end up integrating x to the 2n dx, and that's something a lot simpler that we can deal with. So we have the sum from n equals 0 to infinity of negative 1 to the n over n factorial. Here we have x raised to a power, so we are going to add 1 to the power and divide by the new power, which will give us x to the 2n plus 1 over 2n plus 1. Since we are integrating with a definite integral, we do need to remember to add c. Now this is our power series representation, but we also need an interval of convergence. So let's see if we can remember what sort of information we have when we use integration to come up with a new power series. With both integration and differentiation, but in this case, integration is what we are using, does not affect the radius of convergence. So in other words, the radius of convergence stays the same. Remember that it is possible that the endpoints change, so similar to the substitution or composition that we saw in part A. The endpoints may change, so you'll have to check those individually if you have endpoints, but the radius stays the same, so the interior of the interval is going to stay the same. In this case, the original radius of convergence, which I will abbreviate this time, is, if we look at our interval of convergence that we started with in this case, which is what we ended up with in part A, if our interval of convergence is from negative infinity to positive infinity, that must mean that our radius of convergence is infinity. So our radius of convergence is r equals infinity. If that stays the same, then our new radius of convergence is also r equals infinity, which means that our interval of convergence must be the the same infinite interval from negative infinity to positive infinity. So our final answer here, we're going to have our function, which is this integral of e to the negative x squared dx. This is equal to our series, the sum from n equals 0 to infinity, of negative 1 to the n over n factorial x to the 2n plus 1 over 2n plus 1 plus c. And this is true for all x between negative infinity and infinity. Notice in this case, we are not going to be able to figure out what our undetermined coefficient, or what our constant of integration, our constant of integration is here, because we don't have an actual function here. So we can't plug in a specific x value to get what that c is. But we can just leave it like this for our final answer. I'm sorry, that should be a 0. Didn't really look like that. So here is our final answer for part B of this example.